Great. Good morning, class. Today we'll be talking about systems engineering, specifically timeline, leadership, and requirements. So let's go over program phases. So program phases and mission timelines for small satellites and large spacecraft differ. So I'll go over small space, which is what I'll call small satellite. And then we'll go over the larger phases, larger mission phases, in case you're interested in how to transition that. So this timeline is taken from the CubeSat Launch Initiative Handbook written by NASA. I'm sure that you all will be intimately familiar with that handbook at some point in the future. This is a recommended timeline where concept development occurs for 1 to 6 months and funding to buy your satellite components happens for 1 to 12 months. Merit and feasibility reviews take 1 to 2 months. CubeSat design on paper and analysis with software tools take about 1 to 6 months. Then the development and submittal for a proposal and the response to a CSLI call takes 3 to 4 months. We will span this timeline, these phases, outlined in the blue box, where we will develop concepts and hold merit reviews in class over this semester. Our funding for the spacecraft bus comes from the NASA Artemis grant, and funding for a payload and any spacecraft modifications will be capped at a presumed $2,000 per team, which I think will come from the School of Engineering that funds senior design projects. Next semester, we will attempt to fabricate, integrate, and test our satellites as much as possible while developing the CSLI proposals due in November. I think the CSLI proposals should just incorporate the on-paper work that you've done this semester. But I think that the integration and testing will make your design better because it's a more well thought out satellite design. To answer the question of being stuck in the design process, which is over here, I will say, so the question is, do designs never leave the redesigning phase of a satellite design process? And the answer I have is yes and no. If all goes well, the systems engineer and program manager work together to ensure that the design process has a finite schedule. So in that way, no, satellites should not be stuck in a design process. If the process is not held to, though, the development team may be stuck in a loop where they say to management that the design isn't perfect yet, but really all you need to do is meet requirements, which is another way of saying good enough. So I'm going to say this again. When you're designing your satellite, design for good enough. That's how you get out of design iterations. And the good enough is defined by your requirements. You're only designing to meet your requirements. Anything above is nice to have, but you shouldn't be expending more effort into it. Okay. And then the other question is, in relation to the EPET track, would there only be 6 months for development of the CubeSat if we were to apply for CSLI? The CSLI proposal is due in November, typically. I think because of COVID last year, the proposal was due mid-December. But think about it, right now it's almost the end of January, so we have about 10 months to really flesh out the concept, design, and I think we'll have time to do some playing with hardware. Okay, now let's talk about big space. So for the Orion spacecraft, this concept development happened as early as April 2005, which is over here. So this project is only coming to fruition now, nearly 16 years later. I took this screen grab just a week ago. The Orion Systems Requirements Review happened a year after the beginning, and the preliminary design review 2 years after the system requirements definition. So you can see those review phases are definitely inflated compared to the small satellite program timeline. Granted, this kind of large project is magnitudes more complex than our CubeSats. Not only do we have to worry about people, the government was also juggling commercial relationships and cross-agency and NASA center collaborations. This project also had to endure multiple administrations and groups of leadership, which affects timeliness. NASA just announced that the Orion spacecraft used for the Artemis 1 mission has completed its time in the Neil Armstrong Operations and Checkout Building, which is what you are seeing on the right. The spaceship was hoisted from the stand in that building where it was outfitted with components and systems were tested to ensure it was mission ready. With assembly complete, the spacecraft has been moved to the NASA Exploration Ground Systems team responsible for processing the Orion spacecraft for its launch later this year. So you see that in the CubeSat timeline, it can span 1 to 2 years. For this, we're seeing beginnings as early as 2005, and now it's 2021, so it's been 16 years. Let's talk about another example, not quite as big as the Artemis program. The MAVEN mission, which stands for Mars Atmosphere and Volatile Evolution, is a spacecraft developed by NASA to investigate the upper atmosphere and ionosphere of Mars and how the solar wind strips volatile compounds from this atmosphere. This research gives insight into how the planet's climate has changed over time. The project cost for MAVEN was about $582 million to build, launch, and operate through its 2-year prime mission. MAVEN was a part of the Mars Scout program, and if you remember last time we talked about Discovery-class missions, this is a comparable size mission. The Mars Scout program was a NASA initiative to send a series of small, low-cost robotic missions to Mars, competitively selected from innovative proposals by the scientific community, capped to $485 million. Although MAVEN costs $582 million to build, launch, and operate, it was nearly $100 million less than originally estimated. So that goes to show that not all NASA projects are overrun. Of this total, $367 million was for development, $187 million for launch, and $28 million for the 2-year prime mission operations. Compare that to, let's see, the kits are maybe $5,000 at most, and then you have $2,000 for payload. Compare that with our at most $10,000 CubeSat. This is magnitudes more. MAVEN was initially proposed in August 2006, and you'll see this timeline over here, but didn't get to the launch pad until 2013, which is 7 years later. MAVEN was originally intended for 2 years of primary operations, yet still continues to gather data today. I also grabbed a screenshot last week of recent news articles from MAVEN data, still going strong 6 years later. Okay, as I said earlier, MAVEN was on the order of the Discovery-class missions. Here I have a screenshot of many Discovery-class missions and Frontiers and solar system exploration programs to give you a sense of operational mission lengths at different classes. So Messenger, for example, is right here. Messenger costed $300 million and the Grail mission costed $375 million. I wanted to give you a scope of how long these missions take on the order of large missions. So if you were to work on one of these large missions from concept to mission operations, it could span your entire career, a decade or two on the development and a decade in space mission operations. But let's go back to small space. Cube satellites are on the order of tens of thousands of dollars in hardware to construct. The duration between Marco's conception to completion of spacecraft assembly was less than 2 years, an unprecedented schedule for any planetary mission to date. This CSLI has a typical duration shown for a month, but it's variable. Sorry, when I was talking about a month, I'm talking about mission operations. A typical duration for a month, but it's variable. It could be up to 20 years because, as we observed before, if a spacecraft is robust and is still producing data, then mission operations can be extended. Finding a ride is really, really hard as a small satellite. So I'm going to answer the question of selection and manifesting. What causes such a wide range of timescale for this step? 1 month versus 3 years is a huge difference. So finding a ride is really hard as a small satellite. For rockets, the satellites or spacecrafts are payload. As small satellites, we are not the primary payload on a rocket. We are the secondary or even the tertiary payloads. There's a chain of commands where the primary payloads dictate the schedule, and we either get booked on the flight later in the schedule or not at all. The launch providers control the schedule. Small satellites are also risky and don't produce as much science, so we are subject to adhering to strict safety constraints to ensure we don't jeopardize the primary payload or astronauts. And I say astronauts because most CubeSats launched through the CSLI program are booted out of the ISS. And to get booted out of the ISS, astronauts have to handle the satellites loaded into the arm. So we want to make sure that there is no chance of harming any astronauts during that process. Okay, so questions about program phases. I think I answered most of them along the way, but one that I haven't answered yet is, given the already dangerous levels of space junk in Earth's orbit that damage satellites and make launches more difficult by the year, isn't NASA shooting itself in the foot by choosing to pursue good PR in this way? I'm not sure about the assumption in this question. I don't think that NASA is necessarily saying that we're doing a great job. I think we all recognize that it's becoming more of a problem. So I think there's more nuance to maybe the way that we present the problem, where we can be making good strides in technology to mitigate space junk, but it's still a problem that we face moving into the future.